So here we are going to go over a general mechanism for EAS reactions. Now, recall that an EAS reaction is an electrophilic aromatic substitution, and it involves having a very, very electrophilic molecule that's going to be able to break that aromaticity of your aromatic molecule. Now here, for simplicity, we are using a benzene ring as our aromatic molecule, but in reality, you can have other aromatic molecules in this mechanism. We are just using these for simplicities. Now, if we take a look at this reaction, it starts off with our aromatic ring, and one of those pi bonds is actually going to break aromaticity and reach out and grab that very electrophilic molecule. This electrophilic molecule is actually bound to another atom, but for now we're just going to refer to it as A, and we'll go over this in more detail when we discuss the catalysts and specific examples for this reaction. So one of the conjugated pi bonds in our benzene ring, it breaks the aromaticity, reaches out for that electrophilic molecule, and it's going to form a bond with that electrophilic molecule. Now, what's really important to note over here is that this molecule right over here, it is no longer aromatic because those conjugated pi bonds are not delocalized all the way throughout the ring. They're only going to be delocalized on this half of our ring. That is because this carbon over here now bears 4 bonds. Now, what's really important to make note of, and something you may have thought of before looking at this drawing over here, is that when this conjugated pi bond breaks aromaticity and it reaches out for this very electrophilic molecule, this electrophilic molecule could theoretically bind to this carbon or this carbon because this double bond is shared between the 2 carbons. So when we lose this double bond, each of these carbons can form a new bond. So this electrophilic molecule could have gone here or it could have gone here. I've just drawn it out over here. Another thing to make note of is that this carbon over here, it has 4 bonds. All of these carbons have their 4 bonds, with hydrogen being the bond that is not drawn out. But this carbon over here only has 3 bonds. It has 1, 2, 3, third to that hydrogen. It's missing a bond. It used to have a bond with this carbon, that pi bond, but now it no longer has that bond with carbon because carbon can only have 4 bonds, and this carbon already has its 4. So since this carbon only has 3 bonds, it's going to bear a positive charge. That's really important. And this molecule right over here is referred to our sigma complex, and it is no longer aromatic, and the sigma complex can actually exist in 3 different resonance structures that I've drawn out over here. And whichever carbon is going to have only 3 bonds, it's going to bear that positive charge. Now, instead of drawing out the resonance structures, you can also denote the resonance through drawing out this rhenium ion, in which we simply draw out this dotted line and with a positive charge to denote that the electrons are actually delocalized. Now, going back to our mechanism, recall that yes, we have our electrophilic molecule bound to this carbon. This carbon has a positive charge, but we want to regain aromaticity because this structure right over here, it's not stable. It is not energetically favorable. So in order to regain aromaticity, we need to regain that bond over here between these 2 carbons. But carbon can only have 4 bonds. That means we have to lose a bond over here so we can form a bond over here. Well, how do we lose a bond over here? We can actually lose this hydrogen. When we lose the hydrogen, these electrons will fall back down over here and we will get the reformation of that pi bond. How do we get rid of that hydrogen? Well, we are using a weak base, and this weak base actually came from that original overall molecule that we had where our electrophilic molecule was bound to this other atom. Now, this weak base will go and attack our hydrogen and it will gain the hydrogen, and as a result these electrons will go and the pi bond will reform, and as a result we end up regaining that aromaticity with that electrophilic molecule now bound. So this is the mechanism for an EAS reaction. You start off with your aromatic compound. You have something that is very electrophilic that's going to be able to break the aromaticity, and one of the pi bonds will break aromaticity and reach out for that electrophilic molecule. Once that bond is formed, this is referred to our sigma complex, which is no longer aromatic, and this is very unstable. Due to its instability, and it wants to gain stability, and it wants to gain that aromaticity, that hydrogen will be abstracted, and those electrons will go on to form that pi bond between these two carbons. Now, both of these carbons will have 4 bonds, and that is your electrophilic aromatic substitution. Later on, we will see specific examples of this mechanism and also consider how catalysts play a key role in this mechanism.